Thank you for coming, everyone. So I'm going to talk about global warming and sea level rise. So most of the talk, I'll just kind of review the big picture global one, what's happening to sea level rise and why, from a perspective of global warming. And then the last slide, I'll present some of my own research, which doesn't have to do with sea level rise, but is related to climate change. So just to point out other things that may happen in the future. So this is a slide from our colleagues down the coast at Scripps, where they go to Hawaii, so it's kind of appropriate they go to Hawaii, to measure CO2 in the atmosphere. And this shows the last 2 years, and you can see the ups and downs with the seasonal cycle of CO2 in the atmosphere. And the reason they go to Hawaii is they want to be in a place where the air is relatively clean, so that there's not too much local pollution. But if we zoom back in time and we look at what's happening since they've been taking measurements in the late 50s up to now, even though the air is pretty clean up there, there's a gradual increase in CO2 in the atmosphere globally. And so it's maybe clean in terms of local pollution, but CO2 is a very long-lived gas and is filling up the whole atmosphere. And you can see it increasing steadily. So the ups and downs, those are the seasonal cycles. So at the northern hemisphere, in the summertime, the trees grow and they take up CO2. And in the winter, there's an excess of respiration, CO2 goes back. And it goes up and down with the seasons, but then there's this gradual increase, which is due to CO2 emissions from burning fossil fuels, coal and gas, and somewhat deforestation. And we can step back further in time. Now we go back to 10,000 years, so this is still the CO2, and this is the present. And then we go back to, this is pre-industrial, so now not 10,000, since the beginning of the Industrial Revolution. And you can see a rise, at first gradual and accelerating near the end in the most last 50 or so years, rising faster. And this time I'll step back to even longer, to 10,000 years. So this is 10,000 years ago. This is sort of the present. Zero is 1950, and you can kind of see how unprecedented the increase in CO2 in the atmosphere, having gone up from around 280, maybe 10,000 years ago, to more than 400, and staying above 400 now, ppm, parts per million in the atmosphere. And I show this because CO2 is a greenhouse gas, and it traps heat on the planet, and it makes the planet warmer. And so the next one, we zoom out even more in time, going back 800,000 years, and you can see the kind of the needle at the end. That's the record of more recent times. And humans have been on Earth for maybe the last 200,000 years. We were told a minute ago that people have been living on the islands of the Pacific maybe for 4,000 years, so that's a little gap near the end. But here shows the geography of the Pacific Islands if we can go back 20,000 years ago. And that was during the last glacial maximum. So when the ice sheets on land were very much bigger, the planet was much colder, and you can see that the geography is quite different. This is today up here, and this is what we think it would have looked like 20,000 years ago. I don't know how well known this is, but I'm sure there's some uncertainty. But certainly the islands would have been more and bigger because the sea level was much lower since there was so much more water on land. So CO2 warms the ocean, so I apologize for my non-Pacific centric map. I looked around, but I couldn't find one that was centered on the Pacific, and I had a chance to redraw it. But this shows the surface warming, the trend. So in degrees Celsius per century. And I guess the first thing that catch your eye is that the blue is cooling, the red and oranges are warming, and the whole planet is warming almost everywhere. It's warming more on land and a little bit less in the ocean, and that's because water has a very large heat capacity, so you can store a lot more heat in the ocean without increasing the temperatures very much. So even though the surface temperatures are increasing faster on land, most of the heat is being trapped in the ocean from warming. Maybe 90% of the extra heat has been trapped in the ocean. So warming everywhere. And this shows the heat content, so how much warmer is the top 1.5 kilometers of the ocean. And you probably can't see the numbers, but this goes back to 1970 to 2013, I think. And the axis is the amount of energy in 10 to the 23 joules, which probably means nothing to most people, but it's a lot of energy. And the point is that these records are showing that this is the Indian Ocean, this one, the Pacific Ocean, the Southern Ocean, the Atlantic, and the global. all these trends are showing a warming with time. And the more recent part of the warming, the more recent years, the different records, so there's different methods by which we estimate this, they are starting to converge because we have a lot more data and the instrumental record is much better. But you also see lots of variability superimposed on that. Most of that is natural climate variability. So like the blue would be El Nino years and the beige will be La Nina years. So these large scale climate fluctuations is going to store more or less heat in the ocean. And so when you go back in time, things are more certain, but everything is rising. So the oceans are warming. That's not contested anymore. And then this leads us to what's happening to sea level. So I guess if you warm the planet, you're going to melt ice. And I'm going to go over the processes that do this, but I just wanted to point them out first in words. So as the planet warms, the land ice melts, and the melted water flows in the ocean, and of course it raises the sea level. There's sea ice in the ocean, that's also melting, but that doesn't contribute to any sea level rise because the ice is already in the ocean. At the same time, when the ocean warms, the water expands, so there's something called thermal expansion. And so a certain part of the rise is due to the heat storage in the ocean. So as we store more heat in the ocean, the sea level increases. So these two graphs show the increase, I guess I have a pointer, in the sea level. So this is in millimeters, so up here is 80 millimeters, so about 8 centimeters, about this much, from the period where we have satellite measurements. So we have very good records. So from 1995 over here to 2015, so there's satellites in space that measure the distance from the satellite to the surface of the ocean, the average, and they think we have a very good and very precise record. And the rate of sea level as of July in 2007 is about 3.4 millimeters per year. Those were not used to metric, that's about maybe this much per decade. So it doesn't seem like much, but that's a lot of water if you think globally. And it's the point, if you go back in time to pre-industrial, it just keeps, so this is the tide gauge record, and this becomes more uncertain as we go back. But they kind of agree with each other over the periods where they overlap. So the sea level is rising, and the contributions to that, there's a bunch of them. And I'll try to mention each one. So I mentioned already the density change. So you store heat in the water expands, the sea level increases. So that's one of them. Another one is the land ice. You melt ice, and then the water flows into the ocean, and that fills up the basins also. So this one is potentially the biggest contributor going forward into the future. There's a lot of water stored in Greenland and Antarctica. And when these start melting a lot, there's potentially a lot of sea level from melting ice. Other contributions are mining of water on land. So we drill wells, we pump the water out. Eventually that water flows into the ocean. So the depletion of groundwater is another source of sea level rise. And then there's some completely unintuitive one. The ice sheets are so big that if they start to melt, their gravity, the gravitational attraction decreases. And so the sea level will actually drop close to the ice sheets. And then that means it will rise everywhere else. So right now the water is kind of piled up close to Greenland and Antarctica. And as these melt, that pull from the gravity from these big ice sheets is going to relax, and then the water will flow back to fill the equatorial regions. So all these are different contributions, and then on that there's geological effects that can vary locally, where there's the crust can move up and down. So for those, not so relevant for the Pacific, but for example in Louisiana, the sea level is increasing very quickly, mostly because the land is subsiding. And in Alaska, the sea level is dropping mostly because there's uplift and the land is rising. So these are, locally you might have different variations in what's going on. Globally, the sea level is rising. And then there's other things. Ocean circulation also matters. So if you have strong currents, associated with currents there are pressure gradients, and the sea will tilt. And there may be, for example, over a meter, so a meter is about this high, 1.5 meters or so tilt of the sea surface between both sides of the Pacific Basin due to the big ocean currents. So that also, so if you change the ocean currents, that tilting of the surface is going to change. This is all on very long time scales. On shorter time scales, well, there's tides, there's storm surges, there's atmospheric pressure going up and down. So all these are superimposed on this kind of mean sea level. So if the mean goes up and then you superimpose the storms and the waves, then that's when the catastrophes start happening on land. So this is to show what's happening in Greenland, which is a big contributor and potentially the biggest one in the coming century of sea level rise. So this is work done by a colleague at UCI, Professor Villaconia and Professor Primeau, who worked on these ice sheets. And I think there's a movie, if I can get it started. Yeah, so I don't know if you can see how well. That's time, and you can see if you're sitting close to the front, you can see the little hair on the continent. That's the ice streams flowing into the ocean. And the colors are showing the drop in the height of the ice on Greenland. So this is 0.5 meter down here, and this is 4 meters. So there's been a 4 meter drop in the thickness of the ice on the edges in the past, not quite 20 years, 15 years or so. And so that water is then flowing into the ocean, contributing to sea level rise. So the contributions to sea level rise, I've gone through, but now I'm going to give you numbers. So melting of land ice is a big one. There's about 0.9 millimeters per year from Greenland. 0.9 for combined Greenland and Antarctica. Greenland is maybe 0.75 millimeters per year, and it's accelerating. So if you saw that curve, it's not getting better. The ice is melting, and it's melting faster and faster with time. Antarctica is also melting a little bit in the southern pole. Thermal expansion, so the water getting warmer, is about 0.6 millimeters per year. And then the land hydrology is about 0.4 millimeters per year. All these combined together to lead to some warming. And so the forecast for the future, or what's been happening. So this is from 1800, beginning industrial revolution, year 2000, where we period of instrumental records over here, and these are projections, so these are forecasts. So the uncertainty, of course, gets bigger because we're trying to figure out what's going to happen in the future. But what you see is clear evidence of sea level rise for the period where we have measurements. So this is the knowns, right? Global warming, the knowns, sea level rise is warming. Sea level rise is increasing, and we can measure it. And then the unknowns, I guess, the known unknowns is that it will continue to increase, but how much, there's a big uncertainty. So at the top range out here, that the most recent estimates put at as much as 2 meters, which is about a little bit more than my height. So I live here on the coast of California, not close to the beach, but I suppose if you live in the Pacific Island, 2 meters must be completely scary. That's a lot of water. And then you superimpose storms and storm surge. So I guess the most probable estimate was in this purple region. These are model projections, but there's definitely the possibility of even faster sea level rise with potentially catastrophic impacts. So that's the bit I want to give some orientation on sea level rise, so the known unknowns. And then the last one is the bit what could be, or should be an unknown to most of you, not so unknown to me, is a little bit about my research, because there's all these other potential impacts of global warming. The CO2 goes in the ocean, contributes to ocean acidification, and that impacts life in the ocean, the corals. And here's another thing that nobody's talked about yet. It's from the world of model climate simulation. So this is stuff that my colleague and I and Keith Moore and Jim Randerson and UCI have been working on. And it's a little bit more technical, but I'll try to walk you through it. Something that the models predict will happen out by year 2300, so 200 years in the future. So in the way the present Earth kind of works, in the Southern Ocean, that band where there's water all around the continent, there's upwelling. So the waters flow from depth to the surface. This is kind of meant to be that. This is depth, this is Antarctica, and this is going towards the equator. So the waters flow up to the surface, and they bring with it a lot of nutrients. So the deep oceans are very rich in nutrients. These come up, and then they get used by plants in the ocean that are growing. They use these nutrients. Some of it doesn't get used and then leaks out and flows at subsurface away from the Southern Ocean. That happens in the Pacific, in the Indian, and the Atlantic Ocean, and that feeds the nutrients for the rest of the ocean. Eventually that mixes up, plankton use it, and they grow, and sustains all the life in the ocean. It's the base of the food chain. So in these climate simulations, what we see is a shift in the winds, a very small shift. All the climates show this, that the winds, the westerlies in the low latitude shift a little bit poleward with global warming. And that changes the balance of where the nutrients upwell and how much of them get used in the Southern Ocean. And so the water's up well, the nutrients get used, and by the time they leave the surface, most of the nutrients have been already stripped out by the organisms living there, and the organic matter with the nutrients rains down and goes back to the deep ocean. So what the model shows, and that's these plots are trying to show, that's depth versus latitude. So that's the Southern Ocean, North Hemisphere. And the colors are the amount of nutrients. So this is the present world in the 1990s. This is year 2090 minus 1990. There's not so much difference. But by the time you get to 2090, the blue means a big drop in the nutrients. So the nutrients are being trapped in the Southern Ocean and sequestered in the deep ocean where they're not available for phytoplankton who are growing in the surface. Right? They need light and nutrients. There's light at the surface, but there's much less nutrients. And the predictions are that there would be as much as a 20% drop globally in production of plant life at the base of the food chain, and as much as 60% in the Atlantic. And that's at the very base of the food chain. When you go up from the algae to the small zooplankton that eat it, you lose some of that energy. And when you work your way up to small fishes like anchovies, to bigger fishes, to tunas, each step of the way you lose a lot of that energy. And that efficiency gets worse with a warming world. So we could, if this kind of model-based scenario turns out to be true, there could be drops of more than 25% in the production globally, and more than almost complete shutdown in biological production in some parts of the ocean. So it's kind of alarming, along with the fact that the sea level is rising by a lot. So there's all these known unknowns, and these unknown unknowns, and I don't think it's good to be messing with the climate system that we're doing. So that's the end of my talk. Thank you.
I think we've got time for a couple of questions, if Francois,
Yeah,
if
sure, yeah.
If anyone has.
Yep.
Well, it's a question I often have when I see these graphs where as you go up to the end of this century, there's big
Uncertainty.
variability in the projections. And I always wonder, what is it that isn't known, that could possibly be known, that would narrow that band? Because, what we're dealing with is people saying, okay, it's going to go from X to Y, and the difference is enormous, and then they'll say, we'll prepare for X.
Mm-hmm.
And of course, that's completely irrational, because in other conditions of potential disaster, people prepare for the worst, not for the best. But how do we narrow that gap in knowledge?
Right, I think a huge part of the spread is the decisions we make. So what we decide to do in terms of emitting fossil fuels in the atmosphere, I think that's probably the biggest part of that spread.
Yeah, okay, so it's the uncertainty in how much CO2 there will be affecting these other
that's a big part. And then for the sea level rise, the possibility of catastrophic release of ice from land. So if these large ice sheets were to start breaking off and flowing in the ocean, if we look back in the geological records, there have been times in the past where sea level has risen very, very quickly.
Yeah.
And we don't know if this will happen in the future.
So we don't have that our models of what happens with the land ice sheets aren't as good as we would like them to be.
Correct, yeah.
So that's a big crucial area for research.
Yes, not so much my research, but my colleagues at UCI.
Yes, I know.
Yeah, they work on that, yeah.
I have a question, actually,
Yes.
which occurred to me, but we hear all the time about increasing CO2 levels in the atmosphere.
Yep.
A lot of that is related to combustion.
Yes.
And the depletion of oxygen-producing organisms. But I've never heard anyone talk about oxygen levels in the atmosphere.
Uh-huh.
So what has happened to oxygen levels?
So I'm not so prepared to talk about oxygen levels in the ocean. There's a lot of oxygen in the atmosphere.
In the atmosphere.
In the atmosphere, it doesn't change very much.
Even though it's being turned into carbon dioxide?
Yeah, because there's so much. So the contribution from burning a fossil fuel is using up some oxygen, so it's dropping, it's measurable, but it's not so big. In the ocean, the oxygen levels are dropping, and that's mostly because of warming. So oxygen is a soluble gas. When you warm the ocean, you can't mix in as much in it, and so that is dropping. But that last slide I showed, what got us going on this research is in the model, we showed an increase in oxygen by 2300, which was counterintuitive, and it turned out what had happened was that the biological production had greatly decreased. And so when you do photosynthesis at the surface and you export this organic matter, you essentially, the organisms are burning it at depth and consuming oxygen. So in the future, with less production at the surface and less organic material going down, we were burning, or the microbes were burning less organic material, consuming less oxygen, allowing the ocean to become more oxygenated in the future. Yes. So in the ocean, there can be dramatic changes in oxygen levels, not so much in the atmosphere.
Yeah, so CO2 released into the atmosphere, of course, is related to global warming.
Yeah.
I've also heard about methane, possibly the problem with methane being released as a result of global warming, a triggering effect. Is there any studies on how that might occur? Because there are methane deposits in Siberia and in the ocean, and if those are released, they will accelerate, as far as I understand, the effect.
Yeah.
I don't remember the ratio between CO2 and methane, but it's a higher,
Yeah, methane is a more potent greenhouse gas.
more potent
Yeah.
gas.
It's not as long-lived, so it doesn't stay in the atmosphere as long, but when it's in there, it contributes more to warming. So
Yeah.
I think most of the emissions now are from land, a lot of it from
From
fracking,
Yeah.
from agricultural practices.
Right.
There are some natural deposits, and my understanding is a little bit uncertain, is that the stuff that's stuck in the bottom of the ocean,
Yeah.
if that was to release,
Right.
microbes would consume most of it before it reached the surface.
Oh,
So
okay.
that's the current thinking. But sometimes these things change as our understanding changes.
Uh-huh.
There are some releases from the tundra in high latitudes.
That's what,
Yeah.
in Siberia.
Yeah, so those are releasing.
Yeah.
It's a bit of an unknown how much that will.
Yeah, I was wondering if there are studies that
People are looking into it.
are looking into
Yeah.
it and predicting possible time frame and how it might interact with these other factors.
It's, right, it would be another source of warming.
Yeah,
In addition to CO2.
it's not a good one.
No.
All right, well, thanks very much. That was